Hi, Chemistry. Welcome back to Acids and Bases. Today we talk about bases. So we're basically going to go through everything we went through with acids, but we're going to do it in terms of bases now. So first of all, a definition of a base. We talked through these already. Now would be a good time to pause your video and see if you can name all three definitions. What's the Arrhenius definition of a base? What's the Bronsted-Lowry? And what's the Lewis definition of a base? Okay, so the Arrhenius definition of a base is going to be an OH minus donor. That would be something like NaOH, which in the presence of water dissociates into Na plus and OH minus. The Bronsted-Lowry definition of a base is going to be something like an H plus acceptor. That would be something like ammonia, which reacts with water and accepts a hydrogen from water, leaving that hydroxide base. The Lewis definition of a base is going to be an electron pair donor. And this example would be the same. Ammonia could serve as this example. Ammonia has an extra electron pair. It's going to accept or battle with the hydroxide for that hydrogen. And sometimes, not often, but sometimes, ammonia is going to be successful in pulling that hydrogen off of water, leaving that hydroxide group by itself and forming the ammonia ion. So ammonia serves as a good example for both the Bronsted-Lowry acceptor definition of a base as well as an electron pair donor of a base. So similar to strong acids, you want to memorize what the strong bases are. Basically, it's group 1A and 2A hydroxides. So any alkali metal or alkaline earth metal that's combined with a hydroxide, you can safely assume that it's going to be a strong base. Now, this isn't technically true for all group 1A and group 2A hydroxides. Some of the larger ones down at the bottom are not actually strong bases, but we're not going to deal with those in this class, and you actually don't have to know those exceptions in this class. So if you see a group 1A or 2A hydroxide, you can safely assume that it is a strong base. Any other base you come across is then going to be technically a weak base. Now, here again, we have that designation. When we talk about strong bases, basically we're talking about very strong bases, right? Anything else like ammonia is going to be a weak base whose conjugate is strong, right? So ammonia and ammonium will be those conjugate like weak base, weak acid. Neither one of those is going to be a very strong base. Again, the definition of a strong base is the same as a definition of a strong acid. It's going to dissociate completely and saturate the solution with ions, especially that hydroxide ion, right? And there's not going to be very much reactant left. Now, with that said, bases are not quite as straightforward as acids because some of the group 2A hydroxides, like calcium hydroxide, barium hydroxide, strontium hydroxide, as well as magnesium hydroxide, they are not actually very soluble. When you put it in water, it really doesn't dissociate to a great extent. And a really great example of this is calcium hydroxide and magnesium hydroxide. Now, they don't dissociate. They're not very soluble, right? So when you put them in water, they don't dissociate in water to a great extent, but they're still considered to be strong acids. And the reason I say calcium hydroxide and magnesium hydroxide are great examples is because these are really commonplace examples that you probably have experience with the fact that they don't dissolve. If you've ever eaten Tums, Tums are calcium hydroxide. If you've ever had a Rolade, I always want to say Roloid, but that's a candy, right? Rolade is another antacid tablet that you can chew. That is a combination of calcium hydroxide and magnesium hydroxide. And a third one that you might have had experience with is milk of magnesia. Which is made out of magnesium hydroxide. Now, when you chew these things, if you've ever chewed Tums or chewed a Rolaids or drank milk of magnesia, you know that it's kind of like eating chalk. You chew in your mouth and it's this very like chalky feel. It doesn't actually dissolve like salt, like table salt or sugar would actually dissolve and leave the liquid like a very smooth, clear, liquidy liquid, right? When you drink sugar water, you don't feel like the molecules of sugar still in there. Well, when you drink milk of magnesia, you do. You basically have to take it and shake it up and then drink it real fast, because if you let it sit at all, it's going to separate from solids in the bottom to liquids in the top, and then it's even more gross to drink. So what are you eating when you eat a Tums or when you drink milk of magnesia? You're eating a strong acid. So why doesn't it burn your mouth, right? A strong acid should burn your mouth. Well, it doesn't burn your mouth because it doesn't dissociate very well. It's not soluble. It doesn't dissociate very well in the presence of water. Luckily, because if it did, it would burn our mouth. Our entire mouth would have this like second or third degree chemical burn to it. So these things don't actually dissociate. We can grind them down mechanically, right, with our teeth, but they don't actually chemically dissociate until they hit acid. And then when they react with acid, they act like a strong base. The acid that's in your stomach, that's why you're eating them, right? It's to control the acid that's in your stomach. Sometimes our stomachs get upset because the acid in there is just too much. And so we eat Tums or Roloids or milk of magnesia to calm the acid down. We actually are neutralizing part of our stomach acid so that our stomach feels better. That's exactly what's happening. So all of that to say, they're not as straightforward as acids are. However, you can, like I said before, if you run across a hydroxide that's combined with one of these metals in the alkali metals or the alkaline earth metals, just assume it's a strong acid, strong base. Just assume it's going to act just like any other very strong base would act. It's going to have a very large K. It's going to dissociate into those ions. It's going to react with acids in a one hydroxide to one hydrogen combination, right? So now you know the story behind it. Now you know it's not actually as straightforward as we're going to deal with it chemically, but in our chemical reactions, we are going to deal with these strong bases as if they are very straightforward. Okay, there's my long explanation for you. One other thing you have to know about these are that any of the alkaline earth metals, any of those metals that are in that second family, any of those hydroxides are going to be a double hydroxide. That's this note here. So if you have magnesium hydroxide by itself dissociating, notice that it dissociates into a magnesium ion and two hydroxides. So acids don't do this, right? If we have something that has two acidic hydrogens, like sulfate, for example, when it dissociates, it's just going to dissociate one of those hydrogens, and the other hydrogen will still be stuck to the anion HSO4 minus, right? Well, bases don't do this. Bases don't protonate one at a time. Bases give off all their hydroxides or none of them at all. And so you have to realize that this is going to make a difference in stoichiometry because it's not a 1-to-1-to-1 ratio like the acids are. It's going to be 1-to-1-to-2. This also makes a difference when it's reacting with an acid, which we will get to see those neutralization reactions coming up. But it does make a difference with those neutralization reactions as well, because you're going to need two hydrogens to react with two of your hydroxides to make two waters. And then all of a sudden, and some ions, right? All of a sudden, your reaction's not 1-to-1-to-1 anymore, right? Because that base gives off all of its hydroxide at the same time, and you need enough hydrogens to react with all of those hydroxides. So bases are messier than acids, but you can still deal with them as long as you're kind of thinking about the context as you go. Okay, so just like strong acids, we can calculate the pH of very strong bases as well, and this happens in very similar ways. So let's do this example. Calculate the pH of a 5 times 10 to the negative 2 molar sodium hydroxide solution. So just like acids, we're going to set up the reaction, the K, the ice chart, right? What we want is pH. And so we need to get to the end where we have an H plus concentration, or we have a hydroxide concentration that we can use to get the H plus concentration. So let's set up our reaction, our ice chart, our K, and then we'll go from there. Now would be a good time to pause, see if you can set those things up, and then compare to what I set up as well. Okay, so here I am now. Actually, this is a strong base, so I set up the KB equation, but since it's strong, I probably don't actually need the KB equation because my change is just going to be all of it, right? I should probably do that in a different color since that is not given information. That is information you're going to get from knowing the context. And so we don't actually need this KB equation. Also, the denominator of this is going to depend on the state of this NaOH. If it's an NaOH solid, it's not going to be in the KB equation. If it's an NaOH aqueous, then it will be down here. So you have to be careful of your states when you're dealing with this, right? But in this case, we don't actually need the KB because it's a very strong base. It's just going to dissociate completely. And so I'm going to get my amount of hydroxide here. Now I can do this a couple different routes. I can plug this into the POH, and then I can subtract POH from 14 to get my pH, or I can go POH, the OH ion, into the H plus ion, and then plug that into pH. So you can do this either way. You should get the same answer either way. So let me get an answer for you, and you can compare yours to mine. So for pOH, I got 1.3, and we're keeping 2 sig figs. So my pH is 12.7, or if you're just keeping 2 sig figs, you might round that to 13. Okay, so again, pretty straightforward, right? Really similar process to strong acids. Notice that our base only had 1 hydroxide in it, so our ratio does come out to 1 to 1 to 1 on this one. But if we were dealing with a hydroxide of an alkaline earth metal, our stoichiometry wouldn't be 1 to 1 to 1, and we would have to take that into consideration. Okay, one other thing I want you to notice before we move on and do the same thing for a weak base is my equation. Notice when I wrote my equations on the last slide, I had 2 examples. One of them was NaOH, and one of them was NH3, right? So when you look at these 2 equations, you may notice that the strong base does not include water. So when we were talking about acids, our very strong acids, we could write them as dissociation reactions, but a more correct way would be to write them as if they were a reaction with water. Well, that's not the case for very strong bases. Very strong bases are truly a dissociation reaction, right? Remember, very strong acids like HCl or H2SO4, those are technically polar covalent compounds, right? So the bond that's being broken there is a polar covalent bond. Not so with our bases. NaOH, that's an ionic compound. So the bond that's being broken here is actually an ionic bond. We're going from a lattice into separate ions. And so it truly is a dissociation reaction. You really can't write this with water. Now, that's different for ammonia because ammonia is a molecular compound, right? The bonds in there are polar covalent bonds again. It's not an ionic compound. So this one, you have to include water because it truly is a reaction with water. So you may have noticed those slight nuances with the reactions. If you didn't, now would be a good time to point them out. Might be good as far as like wrapping your brains around these concepts to do a comparison chart. What's the similarities and differences between writing reactions for strong acids versus strong bases? What are similarities and differences between the compound of a strong acid versus the compound of the strong base, or the behavior of the two? What about strong bases versus weak bases? What about strong acids versus weak acids? We have a lot going on there, and kind of sorting out what's happening and how they act and how they exist and why. Those are really healthy concepts to sort out. Just a thought. Okay, let's do this with bases. So we can write general equations for strong bases and weak bases. We just did it, right? For sodium hydroxide, we see that what we have here is a metal hydroxide. If you're dealing with a alkaline earth metal, you're going to have a metal hydroxide doubled. And what you get out of that is the hydroxide ion, or in the case of alkaline earth metals, you get out 2 hydroxides plus your metal ion, right? So those 2 would be our general equations for a base. And then they would lead you to different Ks. Also, notice that the Ks we're talking about in these cases are KBs because they're Ks written for a base, right? So the KB for an alkali metal would look like this. And then again, you may or may not have your actual metal hydroxide on that base. It's going to depend on the state. Is it aqueous or is it solid? For an alkaline earth, your KB is going to be slightly different. You'll have hydroxide squared, your metal ion, and again, possibly your metal hydroxide, depending on the state. All right, so those would be general equations for base, very strong basic reactions. If they give you a KB, if they tell you your KB of magnesium hydroxide is some number, that means you must write a reaction that matches the KB. So in the case of magnesium hydroxide, it's going to be the dissociation reaction of magnesium hydroxide, which results in hydroxide production, making it a KB because it's resulting in a basic solution, right? Now you can also write a general equation for a weak base. Let's see how this works out. Okay, so this isn't going to be quite as straightforward. Water's going to always be the same. Hydroxide's going to always be the same. But then your molecule is going to be different. So I'm not sure what we would represent molecule by. What letter don't we use very often? That's also not an element. How about, oh, good heavens, everything I can think of is already an element. All right, how about we use an NM? It's not a great one, but we'll take it, okay? If that's our variable, then on this side, you're going to have that with a hydrogen attached and probably a charge. So again, the general equation is probably not as straightforward because this can be any molecule that can act like a base, that can battle that water for a hydrogen, right? Your KB in this case would be that nonmetal that has won the hydrogen. We'll say it's charged with your hydroxide. And on the bottom, you're going to have just your nonmetal as long as it's aqueous, right? If it's a solid or a liquid, you don't include it. And then water automatically doesn't get included either because it's a liquid. So again, if they give you a KB, you're going to have to write the reaction for the molecule as if it's acting like a base and resulting in hydroxide. And so that's true if they give you a Ka of HSO4 minus and a Kb for HSO4 minus, you would have to write that reaction two different ways. Write the reaction as if it's acting like an acid, write the reaction as if it's acting like a base. This would be good practice. Pause it here and see if you can write the two reactions. So acting like an acid, oops, that's a negative. It's going to react with water and donate a hydrogen. So H3O plus SO4 2 minus. Acting like a base, it's going to accept a hydrogen. Okay, so notice I can take something like HSO4-, which is amphoteric, just like water is amphoteric. There's a couple compounds that are amphoteric as well. Something that can donate a hydrogen and also accept a hydrogen is going to make it amphoteric. So I can react it with water and write that reaction as if it's going to go both ways. Now, which way is it more likely to go? Well, you would have to probably look at Ks and also evaluate your products. We can see at the bottom that H2SO4 here is a product, and it's also a very strong acid. And we know very strong acids immediately just dissociate their first proton, their first hydrogen ion. And so this reaction isn't going to go this direction. It's going to go the opposite direction. So this Kb would probably be super, 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 super tiny if it's existent at all. So off of this, the take home off of this, the skill off of this to evaluate is, can you write an equation for something that acts like an acid and acts like a base? Can you write both of these equations? That's an important skill, because if you're given the Ka, you need to write it as if it's acting like an acid. If you're given the Kb, you need to write the reaction as if it's acting like a base. That's a good skill to practice. A couple other things that can act that are amphoteric like that. H2O, we already talked about. Another one would be H2PO4-. That one's going to be amphoteric, and so is HPO4 2-, also amphoteric. So if you want to practice this again, those would be good molecules to practice with. Okay, so here we kind of have the flip situation. We did the pH for a strong base, a very strong base. Let's do it here. We want to calculate pH. 15 molar solution of ammonia. They give us the Kb in this equation. So now would be a good time to pause the video, see if you can beat me to the end. I am going to start by writing out my reaction. They gave me the Kb, so I want to write ammonia as if it's acting like a base. It's going to be a hydrogen acceptor, resulting in a hydroxide in solution. They give me an initial molarity for ammonia. Now, I know that ammonia is a weak base, and so because it's a weak base, I don't know what the change is. So I have to use X. I do know, however, that it's going to go forward because I have no ions present, and so my Q automatically would be 0, which makes it smaller than my Kb, which means I must have a forward reaction. My Kb equation, they give me the number here, and I can write an equation. I always write it as plus up there, but it's not a plus. These two things are being multiplied. They each have a coefficient of 1, so I have no subscripts. And I'm going to assume ammonia is aqueous because they haven't told me otherwise, and ammonia would be very strange to have ammonia as a solid. So if I have to guess, I'm going to guess the more common form, which is going to be a liquid in their case. Now, the top are just two x's. The bottom is going to be 15 minus x. So I have a fairly small Kb. I'm going to make that approximation to assume it is going to be a forward reaction, but it's not going to shift very far forward because Kb is so small that ratio of reactants to products is not going to result in very many products. So I'm going to assume that K is going to be so small that it's not going to significantly affect my 15, so I'm going to ignore it. And then I can check my assumption when I'm done. So let's go ahead and do this calculation. All right, 1.8 times 10 to the negative fifth times 15 is 0.00027. I'm going to take the square root of that. So I get 0.01643-ish significant figures, which is X. So now X is my hydroxide concentration. If I plug that into negative log, I get 1.78. All right, and that's my POH, but I want the pH. So I'm going to take 14 minus 1.78, which is going to equal 12.22. I technically can only keep 2 sig figs here, so my pH would be 12 or 12.2 if you're keeping 3 significant figures. Okay, so again, although bases are a slightly more complicated creature than weak acids, the process looks identical, right, to finding the pH for a weak acid. I would say the toughest part of this is going to be writing your reaction out, since they just give you a KB and they don't actually give you a reaction. That can be a tricky part of this. Also, remembering to make the approximation, right? And we can check too, double check that this is less than 5% of my initial quantity, which it is. So I can actually make that approximation. Okay, so the pH is going to be very high. 12 is a very high pH. But again, does that mean that my substance is very strong? Or does that pH more reflect concentration than it does the strength of my base? And that's very true. Yeah, that pH is going to reflect my concentration a lot more than the strength of my base. Another interesting fact about ammonia is a really common lab ingredient. It has a super strong smell. Actually, if ammonia is too concentrated and you smell it directly, right, instead of wafting it like you're supposed to do as chemists, this is a really good example of the wafting rule, because if you smell ammonia directly, your nose is a direct link to your brain, and ammonia can actually go into your nose and make your brain bleed, and it can knock you out. So you definitely want to remember to waft instead of smelling directly, especially when it comes to ammonia. Also, when you find bottles of ammonia, you may see them labeled as NH3, or you see them labeled as NH4OH. So this is actually how our bottles of ammonia come labeled when we buy them from our chemical distributor. Our bottles come labeled as NH4OH. So what do you think is a more accurate labeling? And I would argue that NH3 is a better labeling, because more of what's in the bottle is actually NH3, right? This reaction does not proceed very far forward. This reaction is going to be left with about 15 molar ammonia, because when we subtract off that change and round off to 2 sig figs, we still have 15 molar ammonia. It really doesn't shift forward very much. So interesting side note there. Once you start getting into labs and looking at labels, that one can be a confusing one. Okay, so here's another example of what we just did. We can go through and do this one in class. It's for methylamine. It would also be a good one to practice our organic naming on as well. And we'll do this practice together. We'll do this practice together. And here we are at polyprotic acids. All right, let's talk through polyprotic acids. We've kind of already talked through polyprotic acids a little bit. We've talked through phosphoric acid, we've talked through sulfuric acid, and you've seen that acids are going to protonate one at a time. So this can actually change some ion species because it protonates one at a time and has multiple protonations. So let's take a look at this. If we're talking about H2CO3, so this is carbonic acid, what would the first equation, the first protonations equation be, and the Ka associated with that? What would the second protonations equation be, and what would be the Ka associated with that? So this would be a good time to pause your video and try those, and then come back and see if they match mine. Okay, here's my two reactions. Again, I wrote them as reactions that are reacting with water. You could also write them as dissociation reactions. It's not going to change anything except in your Ka equation, instead of having H3O+, you'll have an H+. Same thing with the second one. You can write it as the dissociation reaction. I'll write that out real fast for you, just in case anyone did it that way. It would look something like that. And again, H3O+ in the Ka equation would then be an H+ if you write it out that way. Okay, so if we look at these two now, carbonic acid is a weak acid. Carbonic acid, it's a weak acid. We can see that from the Ka, right? It's a pretty small Ka. It's even smaller than like acetic acid, which we dealt with on the couple pages back, which was like something around times 10 to the -5th. And so carbonic acid is going to be an even weaker acid. Where do you find carbonic acid? You find it in sodas. This normally forms when you have carbon dioxide and water mixed together. A small amount of carbonic acid forms. And that's one of the reasons why pop is bad for your teeth. Not only does it have so much sugar, which is bad for your body, you're also feeding the bacteria in your mouth, right, which can cause cavities. But it's like doubly bad because it has this carbonic acid present, which will also wear down like the enamel on your teeth as well. So pop is bad. Don't drink it. Drink water. Okay, we can also see that it's a polyprotic acid. So we have a second protonation that goes on here. We have a second Ka. Now, how does the second protonation relate to the first? You can see the Ka is much smaller, like on the order of times 10 to the -4th, smaller than even the first protonation. Ka is larger than Ka2. Ka2 is going to be larger than a Ka3 if there was one, and etc., and etc. So you can see that the strengths of these acids are very, very different. H2CO3, although it's a weak acid, is still a much, much, much stronger acid than HCO3-. And so when we're looking at these successive ionizations, the key to remember is that the first one is so much stronger of an acid that it's really the only one that matters. If you have successive ionizations, you can ignore all of the ionizations except for the first one. You only have to pay attention to the first one because the first one is going to be so much stronger of an acid than anything following it. Additionally, that first ionization is actually going to suppress future ionizations. It's going to suppress all the other ones. And if you look at Le Chatelier's principle, that can actually explain why. And we'll take a look at that in a little bit more detail when we look at chapter 15. So the takeaway from this is that these successive ionizations are so very different. Only the first dissociation step makes a difference in terms of that H plus ion. So you can ignore everything except for the first ionization if you're looking for pH. Now, if you're looking for ion concentrations, it's a different story, and you do have to deal with some of these. Now, figuring out what all the concentrations of the ions are, I mean, look at how many different ions we're dealing with, right? We have our H plus ion, we have HCO3, we have H plus again, we have CO3 2-, we have a bunch of different ions. So walking through this and figuring out how many of those ions you have and what the concentrations of all of them are is a really good exercise to push yourself and figure out, do you really understand how these ice charts and Ks function? However, that is beyond the scope of our class. So if you come up against a question that asks you to find like CO3 2-, which is in the second ionization for an acid, you actually don't need to do those problems because they are beyond the scope of our class. But doing them is interesting. It's a good push for you. And what you'll see is as you calculate how much hydrogen you have from the first ionization and how much hydrogen you have from the second ionization, that you don't get a significant amount of hydrogen from that second ionization. You just don't. You get all the hydrogen you have is going to come from that first ionization. This one will add a little bit of hydrogen to your amount, and then you're going to round off that amount of hydrogen when you account for significant figures. So lots of details and facts to know about polyprotic acids, but in the long run, when you come up against a polyprotic acid, you're going to treat it just like a monoprotic acid, and it really isn't going to change your problem at all. Okay, this is an excellent question. It's going to ask you to calculate pH. So you need that H plus concentration. It's also going to ask you to calculate equilibrium concentrations of all the species. So again, this is the perfect example of something that's a really good exercise. It's going to push you. It's going to push your understanding of ice charts and K equations. Really good exercise for your brain, but it is beyond the scope of our class. So if you want to do this and check to see how you're doing, it's actually worked out in your book. Let me find it for you. It is example 14.15. So try it if you want to, and then check your work against the work in example 14.15. And then if you have questions, we can go through this together in office hours, okay? So just let me know. And that's a good place for us to stop today. So let me know if you have questions on all of this. We'll do practice together. I'll see you in class.